Well, hello everyone once more. I hope you've enjoyed that brief break. I've got myself a cup of coffee here. Hope you have too, or something similar. So pass on to Claire, who'll give us some more housekeeping.
The housekeeper. Sorry if I am repeating myself, but for those who have maybe just joined us, this event is being run as a Zoom webinar, and the link you received is valid for the whole programme. We are recording the event and we will make it publicly available at some point in the near future. If you have any questions for the speakers, please submit these using the Q&A function and we'll answer as many of these as possible at the roundtable later in the programme. Alistair, back over to you.
Thanks very much, Claire. So I'm pleased to move on to the third of our sessions, New Technologies and Methodologies for Monitoring Greenhouse Gas Emissions and Pollutants in Cities. Now, measurement, as we've already heard, underpins much of the decision-making that has to be made these days. In this session, we'll hear from some experts on the science and instrumentation of atmospheric measurement. So it's my pleasure to hand over to Tom Baer, who will chair this session.
Well, thank you very much, Alistair. It's my pleasure to introduce the first speaker, which is Dr. Alistair Manning. Dr. Manning joined the UK Met Office in 1995 and has dedicated his work around atmospheric transport modeling. He initially worked on air quality forecasting, but for the last 20 years has focused on estimating regional emissions of greenhouse and ozone depleting gases using atmospheric observations. Alistair?
Hello, and thank you very much. Let me just get my presentation. Oh. Okay, thank you very much. I hope you can all see that. So thank you very much, Tom, and thank you very much for the kind invitation to join and speak at this event. I'm going to try and set the scene for the new Glasgow measurement network that's going to be set up, and I'm going to set that in the scene of the UK context. Where is the UK currently in measuring greenhouse gases and in its own national network? So what I'll talk about is the National Greenhouse Gas Observation and Emission and Verification Programme, and how cities and the Greenhouse Gas Inventory Programme that underpins what the UK does in terms of reporting its greenhouse gas emissions to the international community. And I'm now going to try and focus that in how do cities fit within the UK emissions totals for CO2 and then sort of set the scene for the Glasgow CO2 emissions. What do we currently know about Glasgow's CO2 emissions? And also to sort of emphasise that cities are really a significant source of CO2 emissions within the UK. And it'd be really important, both on a national and a city scale, to really understand where these emissions are coming from, the size of those emissions, and really more crucially, I suppose, is the impact of a policy change on those emissions. Can we actually detect, the impact of a policy? So first of all, I'll talk about the National Greenhouse Gas Verification Programme that is funded by the UK government. It has a network of sensors. It's called the UK DEC network. And they're all sensors on a tall telecommunications towers, as you can see here. There's 5 of them. And what we do is we draw air down from the top of these towers, which can be up to 250 meters high. And we sample the air at the base of the towers in real time. And you can see on the right-hand side a time series of carbon dioxide measurements that are measured at Tackleston measurement site in Norfolk. And you can see the very strong diurnal cycle of the CO2 observations. Now, this network is used sits within the verification program as a very vital part of understanding the emissions. So the whole idea is to verify what the UK government estimates. So we do this with 3 bits of knowledge, really. We need to have measurements of the atmosphere. We need to understand how the air dilutes as you get an emission. It dilutes in the atmosphere and arrives at your measurement station. So we need an atmospheric transport model. And you can see here on the left-hand side an example of a transport model that we use. And then the other really key point of this is also what information do we have as prior knowledge to help guide the inversion process. We put all these bits of knowledge together, and we try and triangulate to where we think emissions are actually coming from, and we estimate surface emissions and time series. So as an example of that, where we currently do sort of a lot of work is in methane. Methane is emitted from agriculture, waste, natural gas, and wetlands. And you can see here on the top trends, the global trends of methane in the atmosphere. And you can see the red is in the northern hemisphere, the blue is in the southern hemisphere. And you can see there's a strong global growth of methane in the atmosphere. Methane is the second most important greenhouse gas after carbon dioxide. When we look onto the national scale, the UK emissions, you can see in the bottom left-hand corner, the black bars are what the UK estimate in the reported emissions, and I'll come on to them in the next few slides. And the blue time series is what I estimate in terms of using just the atmospheric measurements and trying to sort of verify whether what the UK is reporting is actually consistent with what the atmosphere is seeing. And for methane in these last few years, that has been the the case. So that's really good news for the UK. So in terms of carbon dioxide, though, carbon dioxide, you can see on the top left-hand side, you can see the global, the northern hemisphere in red, and the blue is the southern hemisphere. You can see the strong growth over the last 2 decades. You can see also the very strong seasonal cycle in the observations of carbon dioxide driven by the biosphere, the plants breathing in CO2 and during the summer. And then you can also see on the right-hand side that same time series of carbon dioxide from East Anglia, and you can see the very strong diurnal cycle as well. As basically from a day to night signal, you get a very strong difference between those two. So the most important with CO2 obviously is the most key gas in terms of its impact on climate, and that cities are a really key point of this. And it's in cities where we can make a real big difference in terms of reducing emissions. But CO2 observations are challenging, which these two graphs kind of show, really. They show there's a very strong natural component, and there's also a very strong human component. It's unpicking those two, which is the real challenge of understanding and attributing emissions of carbon dioxide to different sources. So let's talk about now the UK emissions in terms of what they report to the international community. And you can see here, this is the emission map that the UK estimates every year. As Susan Aitken said, it's always 2 years in arrears because they have to collate an enormous amount of information. They have to estimate the activity of each sector in the industries. So like counting the number of petrol cars. You need to have an estimate of the emission per activity, i.e. the amount of CO2 emitted per petrol car, and they report this, and they collate this information for all the different sectors: transport, energy, residential, business, as you can see in the pie chart there, all the different sectors. They collate all this together and submit this to the United Nations Framework Convention on Climate Change. And you can also see here, in this picture, the high resolution that the UK estimates its emissions. But again, as I said, 2 years lag time. And you can see the strong influence of urban areas in that picture. So let's focus in that picture into the Glasgow and Edinburgh belt of emissions. You can see Glasgow there. In the big red blob, and they're where we're going to focus all the effort within the GEMM initiative here in Glasgow. And you can also see slightly outlined in black the Glasgow City Centre region. So if I focus in on that a bit more, you can see here the UK's reported emissions go down to city scale as well. local authority scale, I should say. And you can see here that the estimates for 2014 down to 2018 for carbon dioxide have shown a decline over those years, which is great progress. And you can see the different sectors where they think they've made the impact. So what would be really good is to use the atmospheric measurements to underpin this data and to say, is it correct? Are they on the right track? So just to conclude, really, so the UK submits its emissions to the United Nations Framework Convention on Climate Change, again with this 2-year lag. But the UK has been the first country ever to compare its reported emissions to atmospheric data and report that data to the United Nations Framework Convention. We've been doing this since 2003 when I first did it 17 years ago. So I also showed you that methane, which is the second most important greenhouse gas, and the UK atmosphere and the inventory actually agree for methane in the last few years. In the early 1990s, that wasn't actually the case. But atmospheric CO2 is a really important gas that we need to get our heads around as scientists. It's very challenging, but it's the most important. And as I showed, the UK government, again, estimate emissions on an annual basis, but we need to know how accurate these emissions are. Can they be verified in terms of carbon dioxide for all its different sectors? So again, I'll reiterate the points really that, cities are significant sources of CO2, and it's therefore important to understand where in the city's emissions are coming from, the magnitude of these emissions, and the impact of policy changes on these emissions. I strongly believe that atmospheric observations can help answer these questions. Thank you very much.
Well, thank you, Alistair, for that wonderful presentation, illustrating how the national programs in the UK have provide critical information. In the following talks, we'll hear about how working at the city level can provide even more detailed information about what's going on in those microenvironments. Our next speaker is Professor Ron Cohen. Ron Cohen is Professor of Atmospheric Chemistry at the University of California, Berkeley. He was director of the Berkeley Atmospheric Science Center from 2006 to 2016. Ron is known for his work on the atmospheric nitrogen cycle, the temperature dependence of ozone, and urban emissions of greenhouse gases. He's a fellow of the American Association for the Advancement of Science and the American Geophysical Union. Ron has mentored over 50 PhD students and postdoctoral fellows and is co-author of over 280 peer-reviewed scientific papers. Ron?
Thank you, Tom. So thank you all. It's a pleasure to be able to talk to you today and to speak to you about our approach to observing in cities. You just heard Alistair Manning talk to you about strategies for thinking about national inventories and the role that cities play. And I want to bring you down in scale now to a discussion of what we can do to provide observations at the neighborhood scale within cities. So we also heard this morning about the strong links between California and Scotland. Here's the California side of that. California has set objectives for reducing its emissions. You see in the inset here, the different sectors of California emissions and what would happen if we continued with business as usual. If we did that, we'd be at about 90% of 2015 emissions in 2050. And then that dotted line shows you the trajectory the state is trying to be on.
I'm not sure that Ron, excuse me, I don't know that your slides are advancing. We're not seeing the full presentation. That's working now.
That's working now? Okay.
Yes.
Okay, so now you're, so again, if you can see it here, state is on this dotted line, and state did hit its 2020 target about 2 years early and is trying to stay on this target. And part of the way the state will achieve that target is through the actions in individual cities. So here you see an example, the red stars on the city of Oakland. Right here, city of Oakland is a little less than 500,000 people in a metropolitan area of about 8.7 million people, the San Francisco Bay Area. And with the statewide actions, we'd follow that red line to 2050. So if we're going to meet the state's goal, the city needs to take additional actions internally, and that would bring us along on that green line. So let's see if I can. Okay. So if we're going to understand whether the city is on track to meet its goals and the state is on track, and then internationally in nations and governments within nations and cities, we need 3 steps, as Alistair Manning just told us, to understand what's in the air. We need to be able to make some predictions for what we might be emitting into the atmosphere and how it's moving around. So that's some combination of economic and social data, and then weather models with chemistry. We need observations that allow us to evaluate whether or not the atmosphere is behaving as according to those predictions. And then we need an integrated assessment to circle back and make improvements in those predictions. And you heard Alistair Manning give you an example and say that in the early 2000s, the UK methane emissions were not in agreement with the inventories, or the observations didn't match, and now they do. And that's the cycle that we're trying to promote, that we start with some beginnings of an understanding of what's going into the atmosphere, and then we follow that through all the way to observations and double check. Just as an example, here's the combination of emissions and a model, and you can see the weather here moving around emissions. The largest source you see here is an oil refinery in the Richmond region, right about over here. And this is a 1 kilometer resolution model, and you just saw 3 days of that go by. The goal of the Beacon project and our collaboration with the University of Strathclyde and the City of Glasgow is to be able to measure at that 1 kilometer resolution so that we can provide cities with details of how their CO2 observations and cities. And you heard Mary Nichols from the California Air Resources Board talk about how emissions of CO2 and emissions of air pollution related gases, and you heard from the City of Scotland as well, City of Glasgow as well, the same thing, that CO2 emissions and air pollution related emissions go hand in hand. So what we're doing here is we're making that direct commitment to measure CO2, the nitrogen oxides, ozone, CO, and particles in a way that the analysis then links all of those things together. Example, I can get it to go. Here's the observation parallel to that theoretical movie I just showed you. So you can see here individual locations within the city and the CO2 going up and down as the days go by. I want to give you just a quick story then. Here's the observations from this network in the California region. In purple highlighted the 6 weeks before the COVID-19 shelter in place, and in green the 6 weeks after. And you can see the peaks drop and the change in emissions, and those changes are both because spring occurred and the weather changed that were associated with the shelter in place from this virus. If we add those up and average across the network for individual days, you can see that the biggest changes are at morning rush hour. every single day. What was a very high morning rush hour peak is now much lower. That on the weekends, the changes are much smaller. So now let's just go to the last step here. We have a hypothesis, that's the estimated emissions, but we have a weather model that allows us to synthesize those and make predictions. And then we have the observations. So let's look at what the observations teach us. So before the shelter in place, the observations are able to pinpoint emissions with 1 kilometer resolution, and you can see them along the highways in this region. You can see the bridge connecting Oakland and San Francisco. You can see that there's lots of traffic and emissions at the entry and exit to that bridge. You can also see these point sources that are refineries in the region. After the shelter in place or during the shelter in place, you can see that the emissions associated with all those specific locations have changed quite dramatically. You see them very strongly here along this highway, up along the highway over here at these refineries. Can also look at that by sector. Here's the sectors. We see in black, the total emissions. The total emissions before the shelter in place were as high as 600 tons of carbon per hour. After the shelter in place, they're almost always below 400. The rush hour peaks dramatically lower. And you can see that the variation before the shelter in place was largely driven by the traffic related emissions shown in orange. Those dropped almost in half, 45% decrease, and the morning rush hour peaks are entirely gone. Weekdays look very much more like weekends in terms of the total, slightly more spread out in time. And there were small decreases in the other terms. And as Alistair Manning pointed out to you, in the Northern Hemisphere, in spring, the biosphere removes CO2 from the atmosphere, and you see the beginnings of that in this region. You can see that not only do we get the average over the city, but you get little details about the timing of emissions that are much more fine-grained and allow us to really assess the details of our understanding of the processes. So before the shelter in place, there were quite a lot of traffic-related emissions at night. After the shelter in place, there was almost no nighttime activity. So I've tried to give you a flavor here of what a dense, low-cost network can provide. We've demonstrated that we can have rapid reporting of emissions changes. I showed you observations from May 2020. Those now appear in a peer-reviewed scientific publication that's out this month. So, less than 6 months from observation to publication. That's a rapid acceleration of the sort of timeline that Alistair Manning told you about, where you're 2 years behind on reporting emissions at the national scale. We're able to do this directly from observations, sector by sector. And with only 12 weeks of observations, we can detect 25% changes in emissions. The next step on the science side is to really show that we can change policy-related emissions at the rates that policy is projecting, which are of order 3 to 5% per year. This happened because of an amazing team of graduate students who work with me. And so they're shown here, grad students and postdocs. Again, the network and each individual location on the San Francisco side that I've just shown you. And let me close by just giving you a flavor for the costs of starting this in a new location. We're estimating that to pick up in a new city, it's about $4,000 per square kilometer of hardware. Maintenance about 10% of that per year, and 1 to 2 people dedicated to the activity per year, and then a commitment to collaborate with other cities. So with that, let me turn it back to Tom Barrett to introduce Craig Michie, who will be able to talk to you about the installation of a network like this in Scotland. Thank you.
Thank you very much, Ron, for that wonderful summary of your world-leading research in this area. The next speaker is Professor Craig Michie. Craig joined the University of Strathclyde in 1988, researching into optical sensing technology within the aerospace and energy sector. He is currently deputy head of the Department in Electronic and Electrical Engineering. His recent research focus is in data analytics and wireless sensor technology, particularly within agriculture. Craig?
Okay, the gremlins got us there for just a second. Okay, thank you, Tom. Thank you, Ron. And as Ron has just mentioned, the intention that we have is to replicate all of the good work that he's been doing in the Bay Area of San Francisco over here in Glasgow. And what we're going to do is we're going to deploy a network of sensors similar to the way that he has in his region. Now, the gremlins are still here because this is not moving forward for me. Let me just give me a second. All right, okay. Life is not as good as it could be. Right, okay. We seem to move on now, yeah? Right, so what we're saying is we're going to replicate what Ron and his team have done over in California. This is a collaboration between the University of California, Berkeley, GEMM and Glasgow City Council. And the idea is to implement this dense network of sensors that will give similar measurements to what Ron is doing. And in particular, we're going to complement the measurements that the City of Glasgow been making with additional CO2 data. The idea of this is that we're going to use this as benchmarking data that can inform policy, data that supports the decision makers, and also to stimulate a little bit of public engagement. If I skip on to my next slide. Now, the sensors are positioned, or the idea that we're going to position them is that we'll have one in a network of schools that are displayed around the city. And the schools were chosen for a number of reasons. The location of these forms quite naturally into a kind of 1 kilometre square grid, which is about the density that we would like to have to make this network as effective as it possibly can be. But also by placing the sensors at the school locations, what we've got is a natural inroad to a community of people, the students, the pupils at the schools. They're the guys who are going to be leaving school. They're going to be leaving with the impact that climate change is going to have for the next 10, 20 years. So if we can use our network of sensors to engage them in discussion and work with the schools, then that gives us a real opportunity to engage in some citizen science. As well as the schools, we've been chatting to the Glasgow Science Centre, and by the time COP comes around next year, we'll have a number of case studies that we'll be able to present and show how this is making a real impact. So where are we now? The sensors have arrived in Glasgow. This is an example. This is us in the Technology Innovation Centre at Strathclyde, where the sensors are getting their finishing touches. We're putting in the CO2 component that was shipped separately and powering up the sensors, making them communicate back with Ron's team over in California, and just doing the pre-calibration measurements before they go out and become deployed all the way through our schools. The kind of thing that we'd like to get from this is exemplified by this measurement from a report that was published recently by SEPA. And this is a report that was published on the impact of the Glasgow low emission zone. And you can see there are 3 regions here that are the red region, yellow, and a kind of purple region. Each of these correspond to different years. Right, so the red region's 2018, the yellow 2019, and so on. Now, the point about this is a measurement which shows the level of nitrogen dioxide at the curbside and the impact that the low emission zone had. So you can see that in 2018, there was a significant number of times where the emission levels were higher than the city would like them to be. That got a little bit better in 2019 with the introduction of the low emission zone. And really, the big improvement took place due to COVID in 2020. So these are measurements that are currently there. And what we want to do is get stuff like this around the city so that it can really give you the underpinning data, pretty much like Ron has demonstrated over in California, and show what the value of instrumentation and measurement is to this climate change debate. We've already begun this process with some early sensors that were deployed just at the start of COVID. I'm showing here a screenshot from Ron's website over in the University of California. And I've got on that website, we're taking some measurements from a couple of sensors that have already been deployed in Glasgow. And I've shared these with the people within the EEE department and wider within the universities, and already it's stimulating a lot of discussion. This region here, if you can see my mouse moving, this region here is a point where both the instruments that are situated, one outside Glasgow, one's up at my house, and the other one in Glasgow, right in the centre. Both of these showed a complete change in the CO2 emissions over a couple of weeks period, and we were trying to work out what that meant. It did happen to coincide with one of the government policies that asked us to not visit people, not go out, not visit other people's houses, and we're postulating that perhaps that might be the case. The reality is, whether we're correct or not is not really important at this point in time. What we're putting in place is a series of measurements that will enable us to provide the data for us to make commentary on particular policy changes. And that's what we hope to do. So where we are, the schools have been identified and access has been agreed. We've begun the process of doing the site surveys. This has been held back a little bit because of all of the restrictions that we have to operate within the COVID period that we're now in. But we've done a couple, one at John Paul Academy in the north of the city. We've had a look at a number of locations in Strathclyde campus, and we're pretty much ready to begin the rollout of these sensor devices. By the time COP comes along next year, we will have data from across Glasgow, and we'll be able to give a much more detailed report into what the measurements are showing us, and also how we can use those to comment and inform what's going on in the city. And with that, I'll pass you back to Alistair.
Well, actually, I'll step in here, Craig. Thank you again for the update on what's going on in Glasgow. We're very much looking forward to seeing the progress over this next year, and a report on the measurements over this next year at the COP26 event in Glasgow, November 2021. Our next speaker is Professor Lucy Hutyra. Lucy Hutyra is an associate professor in the Department of Earth and Environment at Boston University. Through integration of atmospheric, biometric, social, and climatological data, Lucy is focused on understanding the characteristics and drivers of atmospheric biosphere exchange of carbon dioxide, particularly in cities. Lucy is the recipient of a National Science Foundation Career Award, is a Kavli Fellow, and currently serves on the Federal Advisory Committee for NASA Earth Sciences. Lucy?
Great, thank you. Can you hear me and see my screen okay?
Yes, it's working fine.
Perfect. Thank you so much for inviting me. I'm going to share some thoughts about collaborative networks in this space and how information and knowledge and data sharing can help advance our efforts. And before I go into the measurement networks, I wanted to start by saying something about the urban networks that are in place. And this really builds from some of the discussions that we'd heard earlier this morning. There's a lot of collaborative efforts between the cities where they're turning to one another for peer learning and for collaboration and economies of scale. There are a number of different efforts underway, like the Global Covenant of Mayors, the Compact of Mayors, the Climate Mayors, the C40, which we heard from David Miller earlier, America's Pledge, Sustainability Directors Network, Carbon Neutral Cities Alliance, and this is just a small sampling. And these efforts are incredible. They're trying to tackle the climate problem at the city scale. But one of the challenges that we have is that these efforts have different barriers to entry and different approaches in what's being reported in them. So several years ago, my colleague John Lynn from the University of Utah and we tried to build from these efforts that were happening across cities and partner with them in an effort that we dubbed CO2 USA. In the United States, there are 6 very well instrumented regions that are similar to what Alistair was describing in the UK. And in an effort to leverage the scientific infrastructure with these policies that were happening at the city scale, we received support from the NOAA Atmospheric Chemistry, Carbon Cycle and Climate Program, as well as the Institute of Standards and Technology, to bring these cities together and to try to understand some of the similarities and differences, foster a community between the scientists and the stakeholders, and try to do syntheses. So we've held a number of workshops, which I'll tell you about, some of what we learned from these efforts. And similar to what Alistair was describing, we tried to take those on-the-ground measurements and harmonize them and make them publicly available. I'll share that with you. We also created consistent inventories to try to look at how much of the differences that we're seeing across cities were due to inventories and how that matched or maybe didn't match some of what we were seeing in the atmosphere. We tried to improve on the modeling systems themselves. I won't talk about that today. We applied that in better emissions estimates and then engaged with stakeholders. So I'll walk through these 4 here today and offer some lessons. So let me start up by looking at the inventories. So here's an inventory that my team created. This is for the year 2011, although we've extended it forward in time. This is for the Northeast quarter of the United States, and we're about to release it for the entire continental United States. This is a very nice inventory. It was a tremendous amount of work, and it involved a lot of assumptions, approximations, and corrections to state and federal data to get a resolution of 1 kilometer. Here are 3 other really nice quality inventories that had the same decisions and choices that had to be made to be able to take national or maybe state level data and disaggregate it to get a picture of what's happening at the local scale where most of the policies are being implemented. You can see that these don't necessarily tell you the same story. You can see that the totals are rather different for one another for a year across the same region. And one of the challenges is that they don't, across inventories, you don't necessarily have the same categories that are being reported. And it's not clear if you only look at inventories like this, if policies are working or which one's the best inventory. If we zoom in to New York City, I think I could really highlight this very clearly. Our inventory, which is this one, used roads as a big proxy for spatial downscaling. The ODIAC inventory used population density. The Edgar inventory used a number of things. This inventory is global. This inventory is national. And there are these trade-offs. So inventories alone aren't necessarily enough to be able to assess local policy changes. But the choice of inventory can have a big impact on some of the differences that we might attribute to policy. In the case of New York City, the relative differences across these inventories were approaching 100% on average at a finer spatial resolution, which makes it incredibly difficult to assess policy. So here I'm making an argument that we need atmospheric modeling and atmospheric measurements like we're discussing here, but I'm also highlighting this because the inventory makes a difference in how we subsequently interpret some of the data, and great care has to be taken in some of the consistency there. I also want to highlight that not all cities are alike. This is looking across 16 US states, and what's plotted, each tall bar is the particular state. And for that state, it is the percent of that state's total emissions that's attributable to urban areas. And cities are very different from one another, and states and regions are different from one another. Some cities have power plants in them that can create a profile that looks very different than a city that has very high congestion but doesn't generate power locally. And so some of what we learn needs to take into account some of that context. Finally, we've spent a great deal of effort in trying to think about how these inventories will propagate into the measurement systems. And so this is 25 kilometers across Boston, where I'm located. Downtown Boston is here where the red blob is, and we get out into the undeveloped suburbs out here. I'm going to play a little movie. This movie will show what the net fluxes look like. So this is a balance between anthropogenic emissions and what the ecosystem surrounding the city might be doing. We're starting in May here. In the colder months in this region, you see that electricity and residential heating really dominate in the city. There's a highway that you could see out here. And some of these patterns between lines, points, and area sources can have a huge impact on the conclusions that we draw based on where our monitoring system might be located. In the springtime, the dominance of some of these sectors changes. And by the time we get to summer, you can see that anthropogenic emissions are actually gone in a large portion of this area, where the biosphere can take up some of those emissions. So if we put this together, this has an important impact in trying to look across cities, because there's some idiosyncrasies in what you see in one city that might be surrounded by agriculture and use one inventory versus another city that is arid and is using a different inventory. So we made an effort in this case to harmonize some of those inputs and try to use consistent models. One of the other things we did was try to make the data available and consistent. We created tools that made the data easier to use and available. And here's an example from the Los Angeles area, where you could see all the different data from measurement locations available. Here's Boston, and we've made this data set, and there's a forthcoming publication available so that anybody can access it and attempt to reproduce and reanalyze these data to see if some different conclusions end up being drawn. Finally, I wanted to touch on some of the workshops. And we held 3 different workshops. We had several hundred people attend these workshops. We did one in Washington, DC, one in Salt Lake City, and one in Boston. And these included policymakers, stakeholders, and scientists. And the first lesson that we learned very quickly is that these groups are often asking different questions. And both these groups don't always realize what the needs versus capabilities are. We ended up realizing that some cities had very strong technical capability where they didn't necessarily need a lot of input or observation from scientists, and other cities that wasn't true, or they didn't have a need for that level of detail. It's also incredibly important how we communicate this. In these workshops, we spend a lot of time talking about uncertainty and the need for rapid data and the trade-offs associated with those two. And a message that we heard repeatedly was that CO2 alone was not enough. Many of the policies and the efforts to tackle greenhouse gas emissions reductions were actually motivated by air quality, and that there's a huge value in coupling and considering these together in a co-benefits framework. So from this synthesis effort that we undertook for 3 years, I think we can conclude that there's great care that needs to be taken in comparing across cities, because some of the differences that we might want to attribute to policies may actually be differences associated with inventories or the biological ecosystem surrounding the cities, or comparison years, or all the above. And there are different typologies of cities that will strongly influence what we observe in them, whether there's a power plant located there or the vegetation that surrounds it. Finally, networks like CO2 USA, the WMO IGIS effort, or the GEMM effort are incredibly powerful for policy analysis, data sharing, intercomparison, and harmonization. But the dialogue between the stakeholders that are trying to use the data and scientists has to be continual throughout to make sure that we're asking the right questions and interpreting the data in really meaningful ways.
Thank you, Lucy. I would like to thank all of the speakers for presenting a comprehensive overview, and I will now end this session. Professor Alistair Ferguson and Clara McLaren will explain the next part of the program.
Alistair?
Yeah, Alistair will when he can get his unmute working, which he has now. So thank you. Over to you, Claire. Let me just say thanks for all the speakers and thanks very much to Tom. That was a fascinating session. And over to you, Claire.
Thanks, Alistair. So we have a slightly longer break this time, which is good for me because it's dinner time in Glasgow. So we will break for about 28 minutes. That's right. Yep, 28 minutes, and see you back here at 6:40 p.m. GMT for the roundtable. Thank you.
Yeah, and just before everyone goes, we're gathering together the questions as they come in. So please use the question and answer facility. Tom is actually working with me to filter the questions and to put them into language that I can understand. And then we'll try and answer those questions at the round table. So we'll see you after the break. Thanks very much.